Hey everybody, Mark B here. Just wanted to step in real quick before the actual podcast proper starts just to let you know what's going on here because the part 1 attached to the name might be a little bit confusing. Basically what happened was I sat down with my friend Zeke, who you'll be introduced to in the beginning of the podcast, to discuss the sciences of Mass Effect, good and bad, and what I thought would probably be a fairly simple one-episode podcast ended up turning into a 2.5 hour long conversation about all of the positive and negative aspects of the science as it was presented. So, I decided it might be better to break it up into two separate podcasts so you're not listening to a 2 hour long podcast, because seriously, who does that? And what you got here is the first part where we're going to discuss the positive aspects of Mass Effect science, specifically related to physics and whatnot. And the second episode, which will be coming out next week, will be related to the negative aspects of Mass Effect science and a little bit more of the positives. So, sit back, relax, and enjoy. Hello, everyone, and welcome to Neo Kobe Pizza, the only gaming podcast that floats in soup. My name is Mark B. Joining me today is one of my good, close personal friends, Zeke. How you doing today, sir?
I am all right, and you?
I'm doing just dandy. Today's topic is going to be a little bit different from the other discussions that we've had at this point, as when I mentioned to you the idea of doing the podcast, pretty much the first thing you came up with was the idea of discussing the science in video games.
Exactly.
Before we get into today's topic specifically, why?
Well, part of it simply is just that I'm a science major myself, although I haven't finished the degree yet. I'm working on a degree in physics, and I've always been super interested in mathematical and scientific topics. When I was in grade school, even, I was already I was reading papers about cold fusion and about astrophysics and that sort of stuff. So this has been up my alley for literally decades at this point.
You were reading papers in grade school about astrophysics and cold fusion.
Yes, I was able to read at a college reading level when I was in 4th grade.
Jesus, I was reading fucking Encyclopedia Brown.
I also read those.
I don't know what to say about that, honestly. I mean, that's fucking impressive, but wow, I feel like you might be the most overqualified person I've had on the podcast to discuss these kind of things so far.
I don't know what to say about that either.
You had bounced a couple of ideas off of me insofar as it related to what games you wanted to talk about. And the one that we agreed on to start with, because you had positive and negative experiences with its science as it relates to how it operates within its own world, was Mass Effect.
Correct.
I'm going to make the assumption that most people have a passing familiarity with Mass Effect as a franchise in some capacity or another. But for those of you who do not, the dollar store version of the plot is you play as a character named Commander Shepard, who you can customize from the beginning of any of the games, who essentially is picked as humanity's first Spectre in the multi-alien race conglomeration that exists in the game world. The first human Spectre is a big deal, and the Spectres are sort of a Black Ops-ish organization that works directly for the Leadership Council of the Citadel, allowing Shepard the ability to go and perform various actions with limited judicial oversight. This ultimately gives Shepard the ability to, in the first game, track down and identify the corruption of another Spectre in the group, while also rooting out the threat of a group of sentient spaceships called the Reapers, which makes sense in the game when you play it, I promise. While in the second game, Shepard dies, and then gets better, and has to go and hunt down the Collectors, which are a group of weird bug aliens that don't really talk to anybody, that are also working for the Reapers. And then in the third game, this culminates with the Reapers just showing up and ruining everybody's shit, because nobody fucking listened to Shepard, of course. And ultimately, the game either ends with Shepard saving the universe, changing the universe, or rocks fall, everyone dies. It's one of BioWare's better efforts, comparatively speaking, depending upon what you're coming to the game for. I personally like the storytelling in the franchise. Others do not. It is what it is. But if you have experienced it, you likely have your own opinions, and if you haven't, maybe that will help you figure out if it's a thing for you. You can probably get the whole set for like $10 at this point.
Yeah, they've been on sale on Steam several times, so they should be easy to get.
For me personally, I kind of got into Mass Effect because at the time when the first game came out, it was exclusive to the Xbox 360 at that point, and it was considered to be the big new release that was exclusive to the console, which was a big deal at the time. I had passing familiarity with BioWare as a developer because I had played Star Wars Knights of the Old Republic, as you do. But beyond that, I didn't have any particular attachment to the developer. I didn't think anything particularly amazing of them as a game developer or as a content creator. I just knew that they had made a game that I had played, that I had enjoyed, and that there was this exclusive game that had come out for the Xbox that I really wanted to play because it looked interesting. And it was flawed, to be sure, but by and large, I felt like there was something interesting in the game amidst the not always 100% functional combat systems and inventory management mechanics.
I was more familiar with BioWare than you were, it sounds like. I had played both of the. I think I had played both of the KOTOR games at that point, and although the second one was Obsidian, but still. And I had also played Neverwinter Nights and Neverwinter Nights 2, I think, both of which were BioWare games. But my familiarity with any games prior to that had been pretty limited. So was aware of BioWare as a company. I was like, okay, like they've done some stuff I've enjoyed. The bigger draw for me was that it was a space opera game. And I had not, other than Knights of the Old Republic, I hadn't really seen a role-playing game that was set in such a science fiction universe, and so that piqued my interest.
At that time, the idea of a mass science fiction universe in general in gaming was not necessarily new, but had not really been done very much. Even when there were games that were science fiction oriented, they generally tended to either be more first-person shooter-oriented, a la Halo, Marathon, System Shock, things like that, or they tended to be more grounded, Deus Ex.
Yeah.
So at that point, the idea of the grand space opera, sort of like Star Wars, but with role-playing elements, was not a thing that we had really been exposed to. And I mean, it's not like BioWare's chops weren't established by that point. As you had said, they did Neverwinter Nights. They did Knights of the Old Republic. And they also did Jade Empire, which was not especially well received, but at the very least established that they were in it for the long haul insofar as dialogue development, story development, universe development went. So I could see how them handling that, which was not a thing that games were really doing at that point, would have been really impressive, especially since I think for both of us that was a concept that was kind of interesting. Like, I loved Star Wars when I was growing up, and while I was not a huge science fiction fan, a lot of the staples appealed to me: Star Wars, Alien, Predator, things of that nature. So the idea of a big space opera was interesting.
And for me, it was, I mean, because I had also been a huge Star Wars and Star Trek fan, although Star Trek's a bit different. But for me also, though, it was seeing stuff that felt evocative of, for example, Isaac Asimov, because I had been reading Asimov's books for several years at that point and was very familiar with a lot of his stuff. So seeing things where you have these, galactic scale societies, and the biological and sociological differences between species actually do factor into how the story is written. That's something that appeals to me as well.
I also kind of feel like, thinking about it in a vacuum, Mass Effect is probably appealing to me to a certain extent because of the science aspect of things, like the technological advancement aspect of things. Given the option, when I was younger, medieval fantasy was very interesting to me, but as I've grown older, I find that futurism and retrofuturism tend to appeal to me more as a player. Like, I play the Dragon Age games, and I'm fine with the Dragon Age games, but by and large, Mass Effect appeals to me more as a player, as a fan, to the extent that when Dragon Age Inquisition was announced, I was like, okay, this is the thing we're doing now. This is a game that's going to come out. I'm going to play it, and it will probably be fine. And when they announced the new Mass Effect, I was, yes, good. This is the thing I want to play. When the fuck is this coming out? So it's, I don't know what it is exactly. For some reason, I just stopped caring about medieval fantasy, and the idea of space fantasy just became more interesting one day, and suddenly I'm at the point now where Mass Effect consistently is one of the more anticipated franchises, even though I was not a big fan of the way the original trilogy ended.
Yeah, same here.
I feel like Mass Effect 2 was, in a lot of respects, the best possible game out of the franchise by and large. Mass Effect 3 was a bit too full of ideas it was trying to cram together in a way that made sense and also allowed for the kind of cookie-cutter endings they were going for. And when you're trying to condense a lot of unique and interesting plot threads into one big knotted ending point from which you can do a couple of minor branch-offs, it doesn't come together particularly well.
I also feel like it failed to capitalize on the real potential that the series had given us prior to that point, which is that it had felt, at least, like we were building up a set of choices that over the course of the entire game would have really defining impact on what ending we got. Whereas with the whole war resources thing at the end, it really didn't feel like it defined your ending. It was just whether your ending was good for the ending you chose or shitty for the ending you chose.
Yeah, that's, I feel like, a major concern for a lot of people within the franchise, where even if you liked the way the game did things to a certain extent, it was not the best way they could have handled it because there was a lot of lost variation there. There could have been so much more experimentation, there could have been so much more variety, and they just broke it down to a couple of very basic staples as to how the game could potentially end up. Even with the expanded DLC that opened things up a bit, you only got like a couple of new endings out of it, but it didn't really significantly expand what could potentially happen to the characters, to the world that they existed in.
Right. It felt like Commander Shepard's ending had been written before you started the game.
Yeah, and to a certain extent, I can kind of understand how there's a certain degree of destiny associated with what's going to happen there, the whole but thou must kind of situation. But the last thing a player who's invested 150 to 300 hours in a franchise wants to deal with is the idea that you were always destined to do this, your choices didn't matter, the input you put into it ultimately didn't matter. This was always going to happen the way that it happened, no matter what, and even the choice you make in the end barely matters.
And not only that, but like that when they do give you the ability to go outside the limited set of things where the main difference was the color of the freaking explosion, they slap you down and say, no, bad, you shouldn't have done that. That trying to defy the ghost child thing at the end of the game literally just means you lose forever. And then it's somebody else who wins instead.
Yeah, and while I can understand that at the very least gives you the ability to say, you know what, I defy your expectation, I defy your requirement to do things this way, it also ultimately means that you're failing and you're leaving the problem to somebody else to resolve. Like, giving the player a method that they could have resolved the issue without necessarily doing what the weird ghost child wanted you to do would have been preferable to the only option is to not play, but that means that everybody just dies.
Yeah. I'm actually reminded specifically of the way that Babylon 5 handled the end of the Shadow War arc. I don't know if you ever watched much Babylon 5. It's a really good show if you haven't. Very character driven. But to encapsulate it really quickly for anyone who isn't a fan, there were several, like, super ancient races in our galaxy before humans and the other alien races that are the major players at the time the show is set. But all of those super advanced alien races left for parts outside the galaxy because that's what you do when you're a super advanced race, I guess. Two of them stayed behind, the Vorlons and the Shadows. And they had chosen to stay to be guardians and caretakers for younger races that would appear, such as humans and Minbari and Narn and whatever else. But they had very different philosophies of how you should do that, and the Vorlons were all about order and discipline and obedience, whereas the Shadows were about chaos and challenge and evolution. And the Shadows believed that they needed to help catalyze new conflicts so that those things would act as the crucible of development, which I can see some point behind that. But that meant that they would have these huge wars where, millions or billions of people would die every few thousand years, which isn't super great. The problem is that toward the end of this most recent Shadow War that humans are involved with, both sides start pulling out planet killers and just blowing up planets that their enemy has had any influence on, which is pretty shitty. So at the very end of this conflict, you have both the Vorlons and the Shadows have been tricked into arriving in the same system at the same time with a huge fleet of all of the younger races there. And the main characters basically say, look, we've figured you out. We know what you guys are doing. You're just being these asshole squabbling parents trying to get us to side with you, and we're sick of it. Leave. Go away. We don't need you anymore. And they try to pull a Crucible bullshit on them and basically say, no, we're going to make you choose. And the two main characters, Delenn and Captain Sheridan, tell them straight up, no. And the other races are with us. You'll have to kill us, and those who follow us, and those who follow them, on and on, every race, every planet, until there is no one left to kill. You will be alone, and you will have failed as guardians. And that's a really powerful moment. Like, they really handle it very, very well there, because it shows how this whole guardianship thing didn't work out, and that their time is done, and they need to move on and do something else. They need to go follow their friends that have left and leave the younger races to their own devices because it's time to pass the torch. And that ending is really good and really solid, and it just shows that it really is possible to have rewritten this ending of Mass Effect in a way that would be, that you could have done it that way, that is a possible path that they just ignored for whatever reason.
And I mean, to be fair, it's a slightly different situation just because you have to factor in that the Reapers aren't doing what they're doing for stewardship or guardianship. They're doing it because they kind of eat the people who evolve. So it's not fair. A perfect comparison necessarily, but yeah, it's...
The child thing is meant to be a guardian of some kind.
Yeah, which is really weird that the child thing is also in charge of the things that are eating people, but
yeah.
Whatever, that is honestly the least of that game's problems, narratively speaking.
Yeah.
But I agree that there were better options for how to handle this sort of thing. I agree that this could have been done better. I don't necessarily know how they could have done it, but by the same token, I'm not the one developing this game, so I don't know that falls to me to figure that out.
Yeah.
But yeah, there's definitely a point where you look at what the game is doing and you can kind of say, yeah, this should have been done better than it was.
But I would say overall, and especially if you look at the character stories rather than the background story, I really feel that several of the character stories were very well handled, and in that sense, it's also a lot like Babylon 5, which is super character driven. That you have the story of Morden Solus, and that is this really compelling story of a person who is super convinced of his intellect and ability, coming to the realization that he has made a mistake, a fundamental bad moral mistake, and that he needs to find absolution for this mistake. That's a very compelling narrative. You have you have Samara and her whole dedication to bringing her daughter to heal because she can't help being a monster. That that's a really tragic and compelling story, and the fact that you can't romance her, that's just not a thing, that makes that story actually more compelling rather than less. Even though romance is usually the thing that they do for almost all companions, it was really nice to see this contrast of, no, you don't have to romance a character for them to be super interesting.
To be fair, if I was the sort of person who, every time I had sex, I popped out a weird murderous space rapist, I would probably not want to have sex anymore either.
Yeah. Makes you wonder how the Asari do birth control.
Though, by the alternative comparison, I also appreciated that in Mass Effect 2, you could actually kill Samara and let her daughter take her place. And then, if you attempted to romance her daughter, you died.
Yes, I did very much like the fact that they included that, like, you got what you deserved, jerk.
Yeah, it's not a constant thing, but every once in a while, games will do something that reminds you, see, this is why we told you not to do this. And when they do that, so long as it isn't dramatically game-breaking, I can appreciate it.
It's not as long as it's not envalicious.
Yeah, I don't know, I enjoyed it in Persona 4 when they made you confront all of the girls that you were cheating on if you were cheating on them with each other, too. So
Yeah, but see, that's not... That was just hilarious, is what that was.
That was not hilarious. That was fucking sad.
The chocolate, though. Anyway, so
let us start from the positive perspective of things, as we had kind of briefly gotten into a discussion before this began, talking about the positive aspects of how Mass Effect handles its science. I am not physics-oriented. My science is more in the realm of information security and things of that nature, so I'm just going to kind of let you go with this and toss in contributions where I can.
all right, I'm going to try to make this as approachable as I can because I really do feel like appreciating how clever they were with a lot of things shows just the level of dedication that they had for creating this universe. That they did a lot of really neat things. They did also some kind of dumb things, but a lot of the stuff they did was very neat, and just showing how elegantly they did things is really quite... It enriches my enjoyment of the universe a lot. So the core of Mass Effect, literally what the title itself is that there is a fifth fundamental force in the universe. In physics, we talk about four fundamental forces. The strong nuclear force, which holds the nucleus of an atom together. It's the thing that... the strong nuclear force holds protons and neutrons together. It's the thing that keeps them from flying apart. The weak nuclear force, which is what holds a nucleus together so that you don't have like carbon spontaneously erupting into 12 hydrogen atoms, because that would be really bad.
Considering that we're made out of carbon, I could kind of imagine that being a thing where people just randomly start exploding.
Yes, that would be pretty much it. If you were to suddenly drop into a different universe where the weak nuclear force was a lot weaker than it really is, you would be in deep shit. You would literally start fissioning. You would be your own walking nuclear reactor. Not great.
Can you imagine how religion would handle that concept?
I'm not sure there would be sentient beings to have religion, so I don't know.
That's fair. If you exploded by the time you hit your 10th birthday, yes, I can imagine that would probably remove the ability for people to continue breeding, let alone developing things like organized language and religion and whatnot.
Right. This is more the problem of I'm not sure that you could have, like, planets on which life could come into existence, because planets would be made of stuff that would be fissioning and exploding, too.
I feel like somebody could make a pretty entertaining game out of that, I'm not going to lie.
You might actually. I could see a sandboxy type game where you get to set the laws of physics, like you set the constants that define how strong the various forces are, and just see what happens. See if you can make a universe where stars can come into existence and immediately explode thereafter.
God, this sounds like the worst version of Clearball Space Program I've ever heard.
So anyway, so the like I said, strong force, weak force, the electromagnetic force, which everybody is familiar with. That's the reason you're able to hear me right now, because we're sending something over an electromagnetic signal, and gravity. Those four forces are what defines how all of reality works. And as far as we're aware, those are the only forces that exist. Mass Effect posits that there is a fifth fundamental force, and that this fundamental force is associated with the dark energy phenomenon that astronomers talk about. Real quick digression on dark energy. Dark energy is not called dark energy because we like it's dark and therefore gets in the way of things. It's called that because we just don't know what it is. We can see stuff that makes it look like this stuff is real because it looks like galaxies are starting to speed up away from each other rather than slowing down like we would expect. But we really don't know much about it other than that.
Now, that's come up more recently, especially with the discussion of the Large Hadron Collider and things of that nature. So I feel like that at least might be a concept that casually scientifically interested people might have heard of. Like I've heard about the idea of dark energy and how it's essentially unobservable for all logistical intents and purposes.
It's basically the current physics ideas, and this is right at the ragged edge of my understanding of anything, so I am nowhere near expert. But as I understand it, it's basically you have this force that works. It doesn't do work because it's a warping of the fabric of space-time itself, and so by having things farther apart, you're actually, but then like making space between it. Those two effects, having more space and then having things farther apart, cancel one another out, and so it's not actually making more energy, but it does result in distances getting bigger. So you have essentially this force that is slowly but surely pushing the empty bubbles between galaxies, the empty big spaces between the strands of galactic clusters that make up the really, really large structure of the universe. These bubbles are slowly getting bigger, and as they get bigger, the effect gets bigger as well. So, in theory, if dark energy continues to progress as we've observed it progressing, more or less, then eventually you're going to get to a point where galaxies start to be so far apart from each other that you can no longer send light signals between them, because by the time the light would get to where the galaxy that you sent it to was, that galaxy is now further away than where you started.
Okay.
And this idea, if you may not have heard of this, but this will be something that science enthusiasts have probably heard of. It's essentially the reverse of the idea of a universe collapsing in on itself. It's a universe that slowly but surely is spacing out more and more and more until finally stars are flying apart from each other, and then planets are flying apart from each other, and then planets themselves can no longer hold together, and you start having matter itself ripped apart at the quantum level because space is expanding so fast. And that's called the Big Rip, and it's one of the possible cataclysmic ends of our universe, literally trillions and trillions and trillions of years from now.
Okay.
So, and again, this weird dark energy is this thing where its magnitude becomes... its effects, maybe is a better way of putting it. The effect of it gets bigger the more empty space there is. But by working, it makes more empty space. So it can become this runaway effect of tearing the universe apart if you give it enough time. It just takes a really long time to get there.
So, essentially, that kind of sounds like it's the sort of thing that's going to maintain entropy in the universe, where eventually it'll get big enough that everything will just destroy itself.
Yeah, you'll get to the point where the energy density of the universe, how much stuff you have per per cubic meter or whatever, has dropped to effectively zero, and that's equivalent to a universe that has become empty again.
That's kind of disconcerting.
And the problem is that we really, really, really don't know anything about dark energy. We just know that when we look out at galaxies elsewhere in the universe, and that when we observe, like when we look at ones that are closer to us versus ones that are further away, when you look, out into the universe, you are actually looking back in time because it takes light time to get to us. So the things that are further away, you're also seeing them when they were further back in time, because it took that light so long to reach us. And as we compare the speeds of things that are really far away to things that are closer to us, which means that it's more recent light, we actually see that the things that are closer to us have a higher speed than the things that are further away. We would expect, because galaxies have mass and therefore gravity pulls stuff together. It's why we're able to stand on a planet right now, because that matter lumped together until it made a planet. And matter in general attracts other matter. That's why you can have galaxies that have stars that are held together in a disk, because you hold this stuff in one place. It's why galaxies have clusters, because they're all mutually attracted to each other. We would expect that even though the matter is speeding apart from each other because of the Big Bang, we would expect this effect to be slowing down because gravity is slowly tugging things back into the center again. But the problem is it's not slowing down. The evidence appears to suggest that it's actually speeding up. And therefore they say there's this energy that we don't understand very well, but there must be something that's driving this expansion, and they call it dark energy.
I see.
That's why I opened this with, this is very poorly understood, and the theoretical backing behind a lot of this stuff is still very, very... I wouldn't call it contentious, because it's generally accepted. The evidence shows this thing is there. We just have no idea how to explain it yet.
Well, that's fair.
There are other similar examples in physics. Some of them are very technical, and so I don't know that they would be very meaningful to most people, but there are things like they knew that Newton's laws worked really, really, really well. We've known that since the 1600s, but when we started getting really accurate measurements of, say, the position of Mercury as it goes around the sun, we realized Newton's laws actually break down. They don't describe how this planet is moving anymore, and we don't know why. But there must be some other effect that's making Mercury behave differently, because we can see that it's not in keeping with the laws that Newton gave us. No matter how we correct for this, we're still coming up short. The explanation was you needed relativity. Due to how close Mercury is to the sun, the sun's distortion of space and time actually causes Mercury's orbit to be very slightly different. It's called the precession of Mercury. And technically this effect applies to all of the planets. It's just that all of the others are so far away from it that those effects are like 0.1% rather than being 20% like it is for Mercury.
I see.
And so you have situations like this where there's a theoretical prediction from a model that's well accepted. People know how it works. We have a good idea. And then we go out and gather better evidence, and we find out, no, actually, the model doesn't describe how this behaves, and we don't know yet how to explain it. In the future, there will be some new idea, though people are proposing hypotheses right now. Hypothesis is how people usually use the term theory. That is, we don't know how this works, but maybe this is it. A theory in science, properly speaking, is that we've done some tests, we've gathered evidence, and the evidence seems to point to this. So we don't really have a theory of dark energy yet. We've got a lot of hypotheses floating around, and none of them are really set yet. We'll see how it goes.
It is interesting as a concept, though, like to kind of try to like wrap your head around that to a certain extent.
Yeah. That's why I want to get into physics. Like it's that sort of stuff. Why do particles have mass? What physical phenomenon is it that gives particles mass? That's the whole question behind the Higgs boson. That's their explanation in the standard model for why particles have mass and why that mass is not the same thing for every particle.
So, how does all of this
get into Mass Effect?
Yeah, how does it work and apply within the world of Mass Effect?
So, the reason why I started with these 4 fundamental forces is that Mass Effect posits a 5th force, as I mentioned earlier, that's related to dark energy. Dark energy is essentially the passive, always there field of this new force, which is literally the Mass Effect. It's where the title of the series comes from. The Mass Effect is that there is a energy field that can be manipulated if you have the right materials and know how to do it, which can alter the nature of space-time, more or less, so that objects within it have more or less mass. Now, this doesn't necessarily sound super useful, but if you know the physics equations behind this, this has some very, very profound effects. But first we'll get into how you do it in Mass Effect. In Mass Effect, they postulate this exotic form of matter, which, if you read the Codex stuff, says that it can only be formed when regular matter is exposed to the energy from a supernova. So, in other words, very rare and very difficult to acquire on planets that have anything like conditions that can support life.
Okay.
Because usually if a star has exploded nearby, most of the matter is not going to survive.
Yeah, that makes sense.
You're going to be having a cloud of dust, which, if you see it from a great distance, will glow because it's hot, and it will be a nebula. That's where a lot of the nebulas that we can see in the night sky come from. The Crab Nebula, the Horsehead Nebula, several of these other ones came from ancient, very large stellar explosions, and you can sometimes even see, in the case of the Horsehead Nebula, you can actually see new stars forming out of the gases and dust floating around out there. But if you do have some of this stuff, which they call element 0, I've seen a picture of a periodic table box for this element, which it literally does have atomic number 0. Properly speaking, that means that it's somehow an element that doesn't have protons in it. It's got less protons than hydrogen, which has 1, which in theory means that it's some kind of neutronium, matter made up of pure neutrons and nothing else. How this can be stable, what its nature is, this is all speculative, but that's fine. This is the one thing that they're making up, more or less. The thing with element 0 is, if you run a positive current through it, meaning you force electrons through it, it generates a field of a certain radius, depending on how much element 0 you have, that will increase the mass of objects nearby. So if you had this element 0 block and you run a positive electric current through it, you will feel heavier. You will actually weigh more, even in space. Objects will be more strongly attracted to you than they were before you turned this field on. And if you run a negative electric current through it, then you will get the reverse. You'll have objects that weigh less. They have a smaller mass. And I have to be careful about using the term weight here, because weight, properly speaking, is something that is relative to a planet, usually. We are actually talking about the amount of mass. Usually something in our reality considered fixed. You have just a specific amount of mass, and that's how much stuff you have. With the Mass Effect field, that's not strictly correct anymore. You still have the same amount of stuff, but its mass goes down. This is super important because of the way that certain physics equations work that involve invariant mass. Now, that's a technical term. A lot of people won't recognize what that means, but it's basically everybody's heard Einstein's classic equation, E equals mc squared. But that's not the whole story. That equation is a simplified form that only talks about the mass of something that, for a particular reference frame, isn't moving. So if your reference frame is the surface of the Earth, for example, which is a perfectly acceptable inertial reference frame, and you have, say, a glass sitting on the table in front of you, then from your reference frame, that glass isn't moving around. We call that at rest. But even though it's at rest, the amount of matter that is in that glass is actually equivalent to a certain amount of energy. And that's what E equals mc squared tells you. If you multiply the amount of mass in that glass by the speed of light squared, that will tell you how much energy is in that. This is the reason why fission and fusion bombs are so powerful, because they're turning even a small amount of mass multiplied by the speed of light squared, which is, if you measure it in meters per second, is 2.998 times 10 to the 8th power. So you're talking about, if you square that, then that's going to be 16 orders of magnitude. You're talking like quadrillions of units of energy there for every unit of mass. That's a lot! And that's the reason why when you blow up a nuclear weapon, it has such a big boom, even though it only converts about a tablespoon of matter into energy.
Really?
Yes. Even though you need a chunk of uranium about the size of your fist in order to make a fissile weapon, the amount of matter that gets converted into energy really isn't that much, because you're only stealing a few neutrons from every atom. It's just that when you do that, you're literally turning a certain amount of the mass that makes those atoms heavy into pure energy, and it's just going everywhere. And all of that energy is pent up in just, literally, like I said, a tablespoon or so of uranium goes away.
Mm.
And if you use a thermonuclear weapon, which means that it's fusion, so it's fusing usually the hydrogen derived from water, then that also is only converting a very small amount of hydrogen into helium, but getting a ridiculous amount of energy from it. And that's how nuclear power works as well. It's just that nuclear power is meant as a controlled reaction. We prevent some of those neutrons from messing up other atoms. But anyway, that, like I said earlier, that E equals mc squared, that's only part of the story. The other part of the story is that if you use the full equation, it's actually written out as E squared equals mc squared squared plus p squared c squared, which a lot more complicated equation, but really all it's meaning is that if you want to talk about all of the energy in something, you have to talk about both how much stuff it is and how fast it's moving. Because speed is also momentum, properly speaking, that's what the P stands for. Momentum is another form of energy. And if you tally up all of the mass and all of the momentum of something, that will tell you all of the energy that's in it. This has some very important implications because, for example, photons, the particle that carries the electromagnetic force, don't have any mass. They are massless particles, which is how they're able to travel at the speed of light. But they do still have energy, and that other component, that p squared c squared, that's where that energy is. Photons literally cannot stop moving because they always have to have some amount of momentum in order to have energy, because they can't have any mass.
Okay.
And so this is some of the interesting things that come out of this equation. But the other thing about this equation is it is actually possible to rearrange this whole equation so that you get mass as just like a separate variable. You're essentially pulling it out of both the mc squared and the p term has a mass hidden inside it, because p, momentum, is mass times velocity. But what this means then is that if you change the amount of mass, that mass term is being multiplied by everything on that side of the equation, and energy is the only thing on the other side. Energy is fixed. You can't change energy. That's a conservation law. And there are actually like mathematical formulae that show that if the universe works by particular mathematical laws, and we've seen that it always does, that you have to have energy conservation. You can't just make energy disappear, and you can't just make energy appear out of nowhere. It always has to be.
Right. So the conservation of energy, as I understood it, is basically mass and energy can't come from nothing.
Yes. They also can't go into nothing. You can't have energy that just disappears forever. It has to go somewhere. We frequently think of something like friction, for example, as making energy go to nowhere, but really what it's doing is, if you were to look at the atomic level, you're having atoms picking up energy from other atoms. It's just that doing the equation for literally trillions upon trillions upon trillions of atoms is far too complex for a human to do, and so we gloss over it as this non-conserving force, even though it really is only just a butt ton of conserving forces all working at the same time.
Huh.
And that when you have that whole released as heat thing, what that's doing is that's essentially the gloss of those atoms that pick up that energy from friction. They can't hold on to that energy very well because it's going to go into their electrons. And so those electrons will go to a higher energy state for a little while and then fall back down into a lower energy state. And when they do that, they're releasing energy as light. And most of the light that they're going to give off, because these are very low energy effects, is going to be in the infrared region. Infrared is heat. So that's one of the ways in which stuff gets lost is heat. Heat is also an important thing in energy, because once you have energy that's been given off as heat, it's usually energy you can't get back by converting it into something else, because converting stuff away from heat costs too much energy to do. You spend more energy trying to get it back than you do what you get back from it. Which is one of the laws of thermodynamics that can be summarized as 1, you can't get something for nothing, conservation of energy. 2, you can only break even. 3, you can never win. You can't even break even. You're always going to lose energy to heat. Anyway, getting back to the that equation I was talking about. If you make mass become a variable, that doesn't necessarily damage this equation that has energy all on one side. It just means that you have to start playing around with the other things in that equation to make sure that energy stays constant. And if you do that, you really only have 2 choices, because there's only 3 terms that are distinct on the other side, on the equation side with mass. You have mass, which we're already talking about as a variable, so we can't work with that. You have the speed of light, which is normally a constant as far as we can tell in our universe, or you have velocity. And in the Mass Effect universe, what they've said is, when you do this Mass Effect thing, the thing that changes is not the velocity of the object, it's what the speed of light is inside that Mass Effect field. And so if you increase the speed of light within that region of space, you're actually making it so that, if you increase the mass inside that region of space, then the speed of light goes down to compensate so that the total energy will remain constant. Similarly, if you reduce the mass, then you have to increase the speed of light in order to make this work out. And so then that means that by doing this process on, say, a ship floating above a planet, you can, if you reduce the mass of that ship, you increase its local speed of light so that it's now actually possible for that ship to travel at a speed faster than the normal speed of light, because its speed limit isn't the speed limit of the normal universe. It's done a thing to raise the speed limit.
The one thing that I always wondered about that sort of a concept was that, essentially how the Mass Effect systems would calculate how you would travel between the mass relays. when you look at it in standard science fiction, the computer will generally calculate the travel points from one to the other to avoid having you crash into a planet or whatever. And in those cases, those are generally very soft on how they handle their science. You can just kind of nod and go, okay, whatever, and accept that this computer is somehow capable of figuring this out. But from the sounds of things, insofar as Mass Effect handles how it works with the idea of traveling between these two distances in a short period of time, it makes sense. So it just seems kind of interesting to me, given the greater amount of speed you're traveling at, how the mass relays and the systems that work with them are able to effectively calculate that you're not going to crash into a planet somewhere along the way.
Uh, there's a couple things involved with this one. One is there are actually two different kinds of mass relays. This isn't a fact that's super actively described in universe, although it is, almost all of this stuff is actually discussed in the codex. So if you play the game and you want to find out this stuff, you can go digging, and a lot of it's even voiced by the guy that does the codex voicing. But there are two kinds of mass relays. There's primary and secondary relays. Primary relays are the ones that connect from one system to another, from one cluster of star systems to another cluster of star systems. And they always point one way. It's that you have 2 points, and you can either go from A to B, or you can go from B to A. You can't go anywhere else on those. So they're dedicated lanes. And these are going to be probably the highest traffic ones you have, because they link the various clusters of systems together, and you may need to make several Mass Effect jumps in order to get to wherever it is you need to go. Secondary relays, on the other hand, are omnidirectional. They can point you in any direction, but they only have a limited range. So that means that once you get to the primary relay closest to whatever planet it is you want to go to, you then go to a secondary relay in that general region and use that to get to the specific system you want.
Now, see, I can relate to that in a certain extent because of how internet traffic tends to travel.
It's exactly like that, yes.
There's going to be major hubs, there's going to be your major backbones of the internet, and major components that will dictate specific paths you have to go. But in a lot of cases, the internet is constantly rerouting itself dependent upon what's the fastest possible route, what routes are down at any given moment. So you could find that going to a website is much faster one day than another day because maybe a router is down that was needed that would get you there in, 10 hops. And because that router is down, it increases the overall traffic to 15 hops, hypothetically speaking, which delays the amount of time it takes for the data to travel back and forth, especially if traffic is being less spread out amongst different devices because of the fact that the one is down.
Yeah, this system is very similar to that, except that, as far as I'm aware anyway, it just doesn't have backups. There's only one primary relay for any given region. And this does create bottlenecks, but because the system was designed by the Reapers to control the ways that civilizations grow and spread, they probably intended that. They're also designed, more or less, not to fail. Now, I know that for real engineering, that's not something you can really do, but for the purpose of this sci-fi thing, we sort of give them the benefit of the doubt and say, yes, okay, you can design something that just doesn't fail. Though I suppose they could do maintenance on them after every culling cycle, so I don't know. But anyway, so the Mass Effect relays are a little bit different from the effect that I've been specifically describing here, because the effect that I've been describing, which they're both working on the same physical principle, this Mass Effect, but I've been describing more how, like, the Normandy itself flies around when it's going from one planet to another within a system. And so it has this big Mass Effect core, which actually it's a really big core for the ship's size, so that it can just coast along using its own Mass Effect field as its source of propulsion, rather than having big, flashy, very hot engines, so that it can do silent running, because the whole thing with the Normandy is that it's a stealth ship.
And not only that, it also explains how the characters are able to travel around within a star system without it taking days, weeks, or even months for them to travel from planet to planet.
Exactly. And on top of that, this is one of the things I was going to mention, so thank you. On top of that, it's also how you can explain the fact that interstellar exploration is very slow, but the ability to move around within a system is very quick. They actually were able to make it so that you have a clear, understandable reason why you can't travel from one end of the universe to the other super fast, but you can get from one star system to another fairly quickly. It's that people don't actually have the ability to fly freely between one star system and another. They're dependent on these mass relays that only go to specific places. And if there's just not a mass relay in a place, then we probably won't go there. And it leaves a galaxy that is mostly unoccupied space. That is, I don't just mean that it's mostly places without planets, but mostly planets that nobody ever goes to because they just can't be reached. There's no mass relay on them. And this is a pretty big triumph of design or for writing, I should say, as far as sci-fi writing goes, because if you have the ability to easily travel so that it only takes like a few minutes, say, or maybe half an hour, to get from Earth to Alpha Centauri, then it really shouldn't take you that long to get from one side of the galaxy to the other. Like, that should be something you can do in a couple months. So there's a very, very big problem in most science fiction where the authors just don't really have a good sense of scale, and it ends up having issues like that where, like, the whole plotline of Voyager should never have happened in Star Trek because it shouldn't have taken them 20 years to cross the galaxy. It should have taken them something like a year or two at most.
Yeah, that did seem kind of strange.
Yeah, it's particularly when you look at how big the Federation is supposed to be on a map. The Federation is supposed to be like about a third or more the size of the distance that Voyager has to travel to get from the other end of the Gamma Quadrant back home. So it really shouldn't take that long to get home, particularly with a ship that's fairly new and can travel at near maximum warp most of the time. So yeah, it's just that there's a very big problem with scale, and Mass Effect actually manages to solve it in a way that ties into the plotline rather than causing problems for the plotline. Very impressive. I thought that's definitely a triumph on their part, is just having a tech thing that explains travel in a way that actually fits the scale and contributes to their plot. Yeah, it's very impressive. But there were a couple other things, and some of this I mentioned to you the other night. So when you're hearing about the way that the Element Zero cores, EZO, is how it's usually referred.
I actually want to stop you there for a second, because there's one thing that I thought was interesting about what you were talking about relative to how the Mass Effect drives allow people to travel relative to distance and space and things of that nature. I find it interesting that they kind of use this as a control mechanic to keep the characters within the Milky Way as well, so that you're exploring a fairly extensive amount of space, but it's still just within our home galaxy, more or less.
Right, and it's not just that, but like even within our home galaxy. So estimating the amount of stars in the Milky Way is not an easy thing because we can't look at the Milky Way from the side. We can only look at it edge on, and so we see just this band of stars. But we can estimate very roughly the mass of the Milky Way, and by knowing the mass and knowing the typical distribution of stars, we can get a rough idea of how many stars there are. There's something like 400 billion stars in the Milky Way. And that's not even counting stuff like the Large and Small Magellanic Clouds, which are small dwarf galaxies that orbit our galaxy. And so you're talking about literally billions and billions of stars, And that means that there's like hundreds of millions of stars that are literally just like our sun, like almost indistinguishable from Sol. And that you have millions and millions of stars that are just like Proxima Centauri, a red dwarf. And that like if someone like if you got captured by aliens and then other aliens freed you and they're like, okay, now where is your home planet? We want to take you home. It would actually be really hard to find our star in that enormous sea of stars out there.
Right, and again, that's just within the Milky Way. The
Yeah,
Milky Way is just one galaxy within what has been termed the local group, which has what 47 galaxies in it.
something like that. Yeah. Now, not all of them are as big as the Milky Way. The Milky Way and Andromeda are the two big galaxies. We're the big fat galaxies of this group. But
And then like the next
yeah,
one I think is Triangulum.
yeah, the Triangulum Galaxy, and in our local area, there's also like the Pegasus Galaxy, which is a dwarf. I want to say that it's a lenticular galaxy, but I could be wrong. Andromeda and the Milky Way, though, are like we're definitely the two really big ones. But even still, like if you count up all of those galaxies, now you're looking at something like trillions of stars spread out between those. And that's just our local group, which is part of a supercluster, pardon me, which is part of a cluster, which is part of a supercluster, which is then part of these enormous strands and filaments of galaxies that then form together to make this kind of like they make sheets and filaments and there's just and that's where we're talking scales that even if you represent their size in light years, you're having to use like 10 to the 20th, 10 to the 30th power numbers for light years. So these are just scales that are utterly mind-boggling, and we know that there are hundreds of billions of galactic clusters out there in the universe. That all of the enormous variety that you encounter in Mass Effect is just a tiny fraction of one galaxy, which is a tiny fraction of our local group, which is a tiny fraction of the next larger scale structure, which is a tiny fraction of the observable universe. Like, it's just mind-boggling how huge this all is.
It's a great big universe, and we're all really puny, all just tiny little specks about the size of Mickey Rooney. Since he's retired now, I'm not really sure if that joke works anymore.
That's fair.
I also think it's interesting, like, I wonder how they're going to tie in the idea of us being in the Andromeda Galaxy.
It's a good question. There are a few possibilities. With the Mass Effect relays, the way that those work, unlike the Mass Effect drives, they set up a corridor of space between two things. So you need this infrastructure already in place. But if you have it, you can set up this tunnel, essentially, of very, very low mass space. And then that means that the speed of light inside that low mass space is very, very high, so you can travel super fast. And that's why you're able to get around as quickly as you do. My suspicion would be that at the time that we're entering the Andromeda Galaxy, we have determined either some way of just projecting one of these tunnels just from one end rather than from both ends, or it's possible that they've been able to tunnel and have hit something on the other end that's able to stabilize it. And so they're like, oh, hey, we know there's stuff on the other end now because we've found a way to stabilize a thing with some unknown anchor on the other side. Those would be my two guesses, but I honestly don't know.
Yeah, I'm looking at a screenshot from the most recent EA play that they did hyping the game up, and it looks like there might actually be some kind of a mass relay in Andromeda. I'm not sure how they're going to explain that, to be perfectly honest about it. That's going to be very confusing, I think.
The only thing that I can think of is that, I mean, this is supposed to be set like a long, long time after the original trilogy, when, in theory, the Reapers have either been defeated, absorbed, or integrated. That is, either Commander Shepard took them over, destroyed them, or did the synthesis ending, which I still don't really understand.
We're all connected.
Yes. And whichever of those endings you go with, the technology of the Reapers becomes available to the people of the galaxy. And given that the Asari were crazy, crazy advanced simply because they had access to some Prothean recordings of tech stuff. It seems reasonable to say that if everyone now has access to the creatures that killed the Protheans, that there's going to be some pretty significant technological advances that might allow us to, because like if people know how these are built, that is, we have the Reapers and we have their knowledge, maybe we're able to build new Mass Effect relays.
That would be an interesting concept.
So yeah, that's one possibility. I'm not sure. I don't know.
Yeah, we'll find out more, I'm sure, as the game comes closer to its inevitable release.
Yeah, a couple more things about the Mass Effect travel using an actual starship rather than using the corridors of space between the relays. When you look into a real nuclear reactor, which I've actually had the privilege of being able to do so, here in Portland, Oregon, there is a research reactor at Reed College. I was very fortunate to be able to do a career week thing back in high school where I just did some volunteer work essentially at the Reed Research Reactor. And so I've actually been able to look into the reactor shaft of a real active nuclear reactor. And if you do so, you will see most of the time that unlike what you see in movies, they do not glow green, they glow blue. And there's a very specific reason for this. As we've been talking about up to this point, the speed of light is a limit on things. You can't travel faster than the speed of light. But what I haven't mentioned up until now is that there actually is a reason why the speed of light can go down below the level that we usually think of the speed of light being. When people say the speed of light, what they really properly mean is the speed of light in vacuum. For reasons that are still not entirely clear to me, but as I understand it, has something to do with the electromagnetic effects of having other matter present. When you send light through a material, so like when you pass light through glass or water, the speed of light slows down inside those materials. Light cannot travel as quickly as it would travel in empty space. And in fact, all materials do this. I should say all materials that allow light to pass through them do this. Water does it, air does it. It's just that the effect of air is very small, whereas the effect of water or glass is much higher. It's the reason why when you stick a straw into a glass of water, you can see that the straw appears to bend. It's because the light is actually traveling more slowly through the water, and then when it hits the air surface, it's able to travel more quickly, and that leads to a difference in how long it takes for the light to get to you, and therefore a distortion of how it appears to, how the straw appears to be shaped. If you had only water or only air, there would be no such distortion, and so it would look uniform. So when you have a nuclear reactor, what's happening is, in most nuclear reactors, you have some kind of fissionable material, usually either uranium or plutonium. Plutonium is typically used for reactors that make nuclear weapon material, but it can be used for research or power generation purposes as well. Uranium is more common for generating power from, and you have this uranium, which is the fissile material. It's the stuff that can have its atoms fall apart and release energy by doing so. When these atoms decay, they release a neutron or two or three. It depends on what specific element you're looking at, but they release some number of neutrons. And when these neutrons hit other atoms of uranium, those other atoms become unstable and fall apart, releasing more neutrons. When you allow this to happen without doing anything about it, and you have multiple neutrons being released per atom, you get a runaway nuclear reaction, aka a nuclear explosion. In a nuclear reactor, you don't want that to happen. You want to have a controlled release of neutrons. You want it to be approximately one neutron comes in, breaks an atom, one neutron comes out, which means you need to absorb a certain amount of the neutrons. There's various ways of doing this. You can use control rods, is a term a lot of people will probably be familiar with. If you've watched any nuclear reactor fiction, lots of movies that have nuclear reactors in them will mention the control rods, and control rods are essentially just a rod of carbon that you stick into the middle of the rods of nuclear fuel, and the carbon gets in the way and absorbs some of the neutrons so that it won't, the reaction process will slow down. And carefully balancing the control rods so that you are generating energy and the reaction is self-sustaining, but so that it's not self-amplifying. That's why you need a degree in nuclear engineering in order to operate a nuclear power plant. But one of the other ways of moderating these neutrons is by having a reactor full of water, because the water will absorb neutrons as they're flying out of this thing at very close to the speed of light, and it will absorb them. It'll become heavy water, so water with an extra neutron in it, and then that will decay and release some energy, and everything will be fine. You don't have to worry about having runaway nuclear problems because of these neutrons flying out. But the problem is that these neutrons, like I said, are flying very close to the speed of light in a vacuum. But they're in water, where the speed of light is noticeably lower than the speed of light in vacuum. You can't do that. You're not allowed to travel faster than the speed of light, not just in general, but the speed of light in whatever medium you're located in. So if you're trying to travel faster than the speed of light in water, you have to shed that excess energy somehow. You can think of it, one possible explanation, I don't know how physical this is, but it's a decent way of thinking about it, is that you have a gun, for example, that can shoot bullets at a specific speed. And if you're just shooting into empty space, those bullets will travel at that speed. There's no air to slow them down, there's no whatever else, they can just go. But if you fire that bullet into a forest of steel poles that's very dense, you're probably going to hit a steel pole at some point, which is going to take away some of your energy firstly and also deflect your path. And if the forest is dense enough, it's going to be bouncing off of these steel poles, and therefore if you look at its net speed over these many, many, many collisions, it's going to move more slowly, right?
You would think.
Even though it started off with the amount of energy needed to travel at a really high speed by having all of these really fast collisions with these various objects, the net speed is slow, even though the speed between any one collision and another collision may be pretty fast. So that's one way of looking at why you can't travel that fast. Anyway, point is, you have these various effects that prevent you from traveling faster than the speed of light in the particular medium, and when that happens, you have those particles, the neutrons, the helium atoms, whatever it is that's trying to do this, will release energy, usually in the form of photons, because photons is a really convenient way of releasing energy if you're an atom. And those photons will always come out at a particular frequency based on what the energy was of the particle. In this case, since we're looking at a nuclear reactor, those particles are released with a particular amount of energy because that's what happens when the when the nucleus breaks down, and when uranium splits into whatever its decay things are. I want to say lead is one of them. When it splits apart into its two smaller components, a specific amount of energy is liberated, and that energy is liberated through the neutron. It's just added to that neutron's movement. So you have a specific amount of energy coming in, which then has to be released as a specific amount of energy coming out, and it comes out as this actually rather pretty blue glow.
Which is also what the engines in the Normandy happen to look like.
Yes, it is kind of funny. They do have a glow very reminiscent of an actual nuclear reactor. Most people wouldn't recognize that, but that is what it kind of looks like, even though the Mass Effect core is not at all nuclear in any way. Like, it just doesn't do nuclear reactions. So that is a funny coincidence that you bring that up now. But getting back to that core, if something goes wrong while you're traveling faster than the speed of light, if you have a sudden drive failure, which is very, very bad, I just want to point that out right now. But if you have a sudden drive failure, your ship doesn't just stop moving. Your ship has been accelerated within this bubble of space where the speed of light is very, very high. It's been accelerated inside that, and so it's got a bunch of excess energy from having been accelerated to that high speed. If you then drop the speed of light back to its normal maximum, you're traveling at a speed higher than that. All of the particles of your ship, your body, everything on board is traveling at this higher speed. So if you suddenly have to be dragged back down to the regular speed of light, then just like that neutron that has to shed its excess energy as radiation, you have to shed your excess energy as radiation. So you literally have every atom of your body and every atom of the ship you're flying in releasing hard radiation. The term for this, by the way, in physics is Cherenkov radiation. It's named after the Russian man who discovered it, or named it, I should say. And so you literally have your ship releasing deadly Cherenkov radiation and cooking everyone inside alive.
So it's less flying from the helm of the ship into the command console and more nuking everybody and frying them pretty much instantly.
Yes.
So I guess when they were saying, we can't stop, it's too dangerous, they kind of understated it a little bit.
Just a little bit. You really, really, really don't want to stop a Mass Effect drive while it's in motion unless you're actually slowing down first.
Okay, and this is where we're going to wrap up the podcast for this week. Join us again next week, where we'll tackle the second part of this podcast, including the less positive aspects of how Mass Effect handles its science. Once again, on behalf of Mr. Zeke, thank you all very much for listening. If you want to check out more of my work, go to diehardgamefan.com or markbwriting.com for more of my written work. Head over to Twitter to follow Mark B. Writing or Facebook to follow Mark B. Writing Home. And if you want to follow the podcast, like, subscribe, and share it, check us out on iTunes, Stitcher, Acast, Google Play Music, SoundCloud, TuneIn, or YouTube. Thanks again for listening. And remember, stay safe out there, Junkers.